So in this section, we want to talk about how can we recognize hazards and understand risk. And the little graphic here shows that this mouse has evidently done some sort of risk assessment because he's generated the fact that if he wears a helmet, he can safely obtain the cheese from the trap without having his neck broken. Whether or not this is a valid risk assessment would remain to be seen. So first we'll define what are hazards and look at some hazards, and then we'll define risk and look at some types of risk and try to get a grasp on that terminology. A hazard, simply stated, is a potential for harm. So we work daily with all kinds of hazards, from driving our car to walking in a chemistry laboratory. You can talk about conditions or activities. They can be natural phenomena like weather, can be chemicals in your house or in the laboratory, processes that you're doing, rotovapping or washing your laundry. Anything poses a hazard if there's a potential for harm. Sources of energy are a big potential for harm. Situations and events, so something that might not be a hazard in one situation might become a hazard in another situation. Hazards left uncontrolled can result in injury, illness, loss of property, and or environmental damage. So we talk about the consequences of hazards. A hazard is an intrinsic property. This is a very important concept. It means that it's part of the event, activity, or condition. And if you're talking about a chemical, it is part of the chemical structure. You cannot change the chemical, so you cannot remove the hazard. There's either a potential for harm or there's not. An example, benzene might be considered a flammable liquid, and there's nothing we can do to make it not flammable. Okay? If all chemicals have hazards, then all chemicals have a potential for harm when we're working with them. Obviously, that does not mean that we as chemists do not work with chemicals. They are our tools. We have to learn to work safely with our tools. That would be like telling a construction worker that they could not work with a saw simply because there's a possibility that they might injure themselves with the saw. We have to teach people how to work with their tools. So let's look at a chemical health hazard. And we take three chemicals here: sodium chloride, sodium cyanide, and sodium azide. And we talk about their LD50s. So we're talking about the toxicity of the chemicals, just how toxic is the chemical. And this is by oral route of exposure for a rat. An LD is abbreviation for a lethal dose that killed 50% of the test population. And so you're looking at whatever they tested, whether it was for aquatic toxicity or for human toxicity. Obviously, they're not going to be testing humans for a population for some toxicity. They're going to test it in some sort of animal system and then extrapolate the data for human systems. But for the rat, 3,000 milligrams per kilogram of body weight is considered enough to kill half the test population. So that's 3 grams per kilogram of body weight. So if you extrapolate that to your body weight in kilograms, you can see that it'd be quite a lot of salt that you would have to eat, but that you could actually kill yourself eating salt. For sodium cyanide, it's 6,440 micrograms per kilogram, and then for sodium azide, it's an oral dose of 27 milligrams per kilogram of body weight. So you can see that the last two chemicals there are much more toxic, more potent than the sodium chloride to elicit adverse effects. When we're talking about toxicity, we talk about dose. So what is the dose? And that is the milligrams or micrograms per body weight. So what about risk? Well, we're going to talk about two kinds of risk. One is objective risk, that is risk you can more or less measure. It's still got a subjective component to it because you have to estimate risk. You can't ever really get a finite number value for the risk. Um, you have to use your experience to evaluate it. But the probability of an adverse consequence occurring from some existing hazard is the risk. And it's not an intrinsic property. We can reduce risk by, remember that hierarchy of controls? We can reduce risk by implementing the hierarchy of controls. I usually talk about three components to risk. Some people talk about only two, but I talk about the likelihood of the event, the hazard causing some consequence, the exposure to the hazard, that is, how often am I going to be working with it or something of that nature, and the consequence severity, that is, and we'll look at that here. If you talk about the likelihood, how likely the occurrence of a complete sequence of events, sounds like lemony snickets, leading up to a consequence is upon exposure to the hazard. So what is the likelihood that a hazard will cause a consequence? And it's associated in actuarial. You usually talk about, if you're an insurance person, you usually talk about descriptors such as rare, unlikely, possible, likely, almost certain. And so for chemicals, exposure must be considered you consider the nature of the chemical and how it is being used. Do you have the right uh, uh, controls to be able to use that chemical safely? So if you don't, the risk is higher. Toxicity, the route of entry, chemical form, length of exposure, etc. So what are we talking about here? Route of how toxic is it? We looked at that. What does its LD50 say? Um, what's its route of entry? Most people aren't going to eat chemicals in the laboratory, so that's a very low route of entry possibility. But say inhalation, which is the highest or the easiest way for us to have exposure in a laboratory to a chemical. How long am I going to work with it? Also consider the physical hazards of chemicals. That is, are they flammable? Are they explosive? Are they friction sensitive? Those types of exposures. And then the severity of consequence. Is it going to be that I need a band-aid, or am I going to be in the hospital, or am I going to ultimately die from whatever consequence happens? So if you look at these three entities, you can generate with different mechanisms some sort of uh, uh, score. And if you assign a value to each of these, a numerical value, you can assign, this times, oops, let me go back, this times this times this, and then you will get some numerical value. Some people don't assign a mathematical value. They talk about descriptors of high, medium, and low. I like to do both. So the terms hazard and risk are not synonymous. A hazard is an intrinsic property of a substance or condition. The potential for harm is always present. But by implementing appropriate controls, that hierarchy of controls, I can lower the risk associated with identified hazards. Now, the key there is if I don't identify the hazards, if I just go into the lab and don't even think about what hazards I'm working with, if I don't identify them, I can't apply the hierarchy of controls and lower the risk. Let's look at a simple case scenario. Which has the greater risk of use? If you consume a half a pound of sodium chloride, or if you're driving in a car with an airbag containing 130 grams of sodium azide. Well, we drive in a car most every day, and the mechanism for the airbag is that uh, there's a platinum catalyst, unless they've changed it in the last 10 years. There's a platinum catalyst that, upon impact, it reacts with the sodium azide, and you generate nitrogen gas extremely quickly. And so, in the reaction. So you're always sitting there behind some sodium azide, which we saw in that previous slide is extremely toxic. Salt, table salt, wasn't so toxic, but what if we ate a half a pound of it very quickly? Well, you would unbalance your electrolytes severely and you would probably kill yourself. Whereas working with that sodium azide, it's in some protected component. It's not, even if your airbag goes off, the azide reacts very quickly and it's gone. It converted to nitrogen, so you're not exposed to it. So you can see that two different chemicals, one not so toxic, one very toxic, but yet we use this one, both of these every day, and we know not to eat a lot of salt at one time, and we have protections in place to protect us, barriers in place to protect us from the sodium azide. So another example, benzene is known human carcinogen, and its exposure to benzene in the laboratory poses a health risk. And benzene isn't used so much anymore because it does have such a severe health risk. It's a known blood carcinogen. It causes leukemia. And most people have come up with substitutes for this solvent in the laboratory, but every now and then you have to use it. However, regardless of what the solvent is, and many of them that we do still use, such as methylene chloride or DCM, dichloromethane, if we use it on laboratory scale, which means small amounts, and we're in a hood, then the likelihood of exposure is low or eliminated, and we've used an engineering control, a fume hood, to minimize the risk. So we can work with chemicals that are extremely hazardous to health if we work with them properly. But we have to we have to recognize the hazard, that's the R part of RAMP, and then we have to assess the hazard, and then we have to minimize the hazard by putting controls in place. The final part of RAMP is preparing for emergencies, and we have to do that because no control or set of controls is 100% fail-safe. And so you always have to be ready in case there is an emergency. You don't want to be preparing for an emergency during the emergency. In most industries where hazards exist, projects cannot proceed without a written hazard analysis and risk assessment, compared to academic research laboratories where it's rare that somebody will perform a risk assessment even informally before the research starts. This could be a time factor. I don't have time to do it, as you saw in the video that we previously watched. That's not a very valid excuse. Um, the fact that you don't sit back, recognize your hazards, and assess the possible risks from those hazards leaves you wide open to harm should something go wrong. Why don't we perform, aside from time excuse, why don't we perform risk assessments in research laboratories? One is the changing nature of academic research. It's very dynamic. In industries, uh, majority of industries do one process and they do it all day long, every day. It's rare in academics where you might do something like that. You're usually trying different things out. You're switching reagents and switching ligands on to make new substances, or you're trying out a different solvent. So there's a lack of change control. If the chemicals are there and available, you have an idea, you have an hypothesis, you're going to test it out. You have the available chemicals for doing it, and there's no management controls in place saying, wait, step back, look at how you're changing the process. What hazards might you be introducing that you haven't thought about, haven't assessed? What could go wrong? How am I going to prevent them from going wrong? So here's an example. You have a credit card that you can order chemicals with. You need some hydrofluoric acid. You don't never have used it before. You know it's very hazardous, but you don't have a lab set up to use it. You have to have special fume hoods, you have to have special training. In some locations, I've actually heard you're supposed to tell the hospital if you're going to be working with hydrofluoric acid so that if they get you in with an exposure, they know what to do. It's but the researcher is going to say, I've got the money, I've got the need. I'm just going to go ahead and order that. So let's look at change drivers. That's what we're talking about here. Is this is what makes academics a little bit different than industry. There's lots of change drivers that occur. These are significant changes that can impact the risk associated with an experiment. So if we look at this matrix of change drivers, you've got addition of a new technique. Some of these I've already mentioned. I didn't talk about psychological fatigue. You're stressed, you're under pressure, you're in a hurry, and incidents occur. You have a new piece of equipment you've never used. You're going to scale up the reaction. I've got an old chemical that's not stable anymore. I'm going to go outside my experimental parameters. I need this to be just a temperature to be just a little bit higher. I need the pressure to be just a little bit higher. I'm going to use something I've never used before, new solvents or reactants. So anytime we change something, we need to reevaluate the hazards and we need to determine the new hazards and then we need to reevaluate them. And in the last 10 years, three very significant incidents have occurred based on some of these. One was the Texas Tech incident, which was scale up. The researcher is a graduate student. He scaled up he was working with an energetic material for the Department of Energy or Department of, um, I think it was the Department of Energy, but he scaled up the reaction without confirming the amounts. He went from milligrams to grams, and he was grinding in a mortar and pestle, and he lost some fingers, and I believe he lost sight in one eye. Very significant incident. Another one was a new person or team. This was the incident with Sherry Sanjay in University of California, and this was she actually succumbed to her burn injuries. That's what remained of her clothing on the floor in this laboratory. She was working with a pyrophoric material. And then finally, I'll look at modifications to equipment. This was at the University of Hawaii, and there was a pressure tank that they had modified. This was like they like a compressed air tank, and they were putting methane or carbon dioxide. I can't remember what they were using, but the mixture was flammable, and they had put a gauge on there and modified how it was attached, and there was a spark, and it actually you can see the sharp metal. It severed the researcher's arm, and she survived, but it was a very significant injury. So let's look at subjective risk. We looked at objective risk, where you can talk about a number or you can talk about high, medium, or low. So it can be qualitative or semi-quantitative. And but let's talk about subjective risk. Below are two sequences recorded from several coin tosses. Which one seems more likely to you? And I can't do this activity as I normally would if I was in a group of students, but I will tell you that here we have A, which is H, heads, tails, HT, HT. So it's very symmetrical. And the second one is more random. And most people usually pick B because we expect statistics to be random. That's just human nature. The truth is, both A and B have the same number of heads and tails. The likelihood of each pattern occurring is the same. And actually, you could calculate the factorial, depending on the number of flips you do. If you flip the coin enough times, you're going to get every possible pattern. As I said, most people choose B because it looks random and we expect nature to be random. And each toss is independent, but the truth is, each toss is independent of the previous. The coin doesn't know what it's doing. It doesn't know what it did the previous time. It doesn't know what it's going to do the next time. And the likelihood is 50-50 each time that it'll either be heads or tails. However, we put our expectations and our biases onto probabilities, and that's the subjective part of risk. So we think it's never going to happen to me. It can't happen here. I've done this 100 times and it's never gone wrong. So we put all these kind of our personal risk perceptions onto laboratory activities, and we build patterns based on that, but they may be flawed patterns. One instance I can give you for how this translates to something in the lab. For years, I could not figure out why ethyl ether research. If I go into an organic chemistry lab and ethyl ether, they would have it in the refrigerator when on the bottle it didn't say store at refrigerated temperatures. And so I'd ask, why are you storing it at refrigerated temperatures? And the answer ultimately that I got was, um, either that's the way we did it in my postdoc, or that's the way I learned, or, well, it's a volatile solvent, so the volatility will be less at refrigerated temperatures. But there was never any rationale other than those types of things. Because I always base how I store chemicals on manufacturer recommendations. So that logic represents all heads, right? I'm storing this chemical the way I was taught to store without any real thought into what's best for the chemical. And then one day I open the bottle and the peroxides that have formed detonate. So ethyl ether is one of the solvents that can form organic peroxides. That's chemicals, compounds with the O single bond O structure. And they will precipitate in organic solvents and can make them very dangerous over time. They're what we call time sensitive compounds. And so we want to make sure that we don't let these kinds of solvents sit around in our lab forever. We want to use them up. But if you store your peroxide in the refrigerator, and I'm going to talk about that on the next slide, the logic then becomes tails that last time where it detonated and we have boom. So what happened is what I've already talked about, why we're storing it in there. But if you look at the last um, text, the problem is that peroxides form when ether is exposed to air, and that's how come they're time sensitive solvents, is they form peroxides over time once they're exposed to air. They freeze at higher temperature than the solvent. Thus, the solid peroxides precipitate at the refrigerated temperatures, making the solvent even more dangerous. And so there's no need to store ethyl ether in a refrigerator, even a flammable refrigerator. Those are, all laboratory refrigerators have to be specially designed so that they don't spark um, solvent vapors inside them. And those are called flammable proof refrigerators. But if the manufacturer doesn't have it on the bottle, there's no point in putting it in the refrigerator. It's where would you store it? In the flammable cabinet. It's a flammable solvent. So as we go through the stages of learning, and I don't know if you've ever seen these before, you have unconscious incompetence. We don't know what we don't know. And we move towards conscious incompetence, which is what you'll do during this presentation. You'll realize that you don't know what you don't know. And we get to a point where we might have the knowledge, but we have to think to execute the knowledge. So a lot of times researchers will do risk assessment out of experience, but they don't do a complete risk assessment because they're just basing it on whatever prior biases they had. So up into, and that's like the ether case, up into a point, these will work. But if you change things a lot, you really have to sit back and look at what you changed and how that's affecting what could possibly happen. When you get to unconscious and unconscious competence, you're very knowledgeable in your experience regarding the subject at hand, and the practice is rote. Well, you're still not out of the woods because you can still make a mistake. Humans make mistakes. And so the more you can document risk assessment in your laboratory, the better you'll be. You won't forget a step. You won't, if somebody new comes in, you'll have something written down for them to look at. So I'm not saying that getting to this level makes you perfect. I'm saying that everybody goes through these levels of learning. And ultimately, we're all bounded by our own experiences. Our perception of risk limits our decision making capabilities. We may not have the information we need to make the right decision, but we have to make fast decisions. I once read, if you had to every day wake up and decide based on risk assessment what you were going to wear, you'd never get dressed and leave the house. So we have to make fast decisions, and we have to determine when a decision needs to be slowed down and when we can make a fast decision. We call that the fast and the slow brain. Um, we constantly use what we know to make these fast decisions about risk, and sometimes they're going to be good and valid, and sometimes they're not. So by doing a risk assessment, you have actually thought about the process, and those thoughts will come back to you. They'll become more rote. They'll come back to you as you're performing the activities in the lab. So, how do you make better decisions in the laboratory? And how do we take into account subjective risk? We have to be aware. We have to be vigilant about recognizing change. I'm increasing the temperature. I'm increasing the pressure. I've used a new reagent. So, there's change drivers. You're thinking about that. You have to be accountable, ask questions, challenge coworkers. You have to set limits, meaning I'm going to establish boundaries. I'm not going to increase or scale up this reaction until I've thought about all the ramifications or talk to my PI. I'm going to communicate with all members of the lab group on a regular basis. Have you ever done this? What did you find were the problems? I'm going to write it in my lab notebook. I'm going to report near misses to the people that can actually document them and at least put them in your lab notebook so that if the next person is doing the same thing, they know that there's a problem that can happen. You're going to be transparent. So you're going to talk about these with your supervisor and other workers in the lab. Don't try to hide near misses and incidents. It's important that you understand why they happened so you can correct it for the next time. And you're going to manage risk, which means you're going to perform a hazard analysis and risk assessment. And so that's what we'll talk about in the next section.